Hey guys, I chose to make a video solution for 3/17 because this unit is pretty hard, or this question of the week is pretty hard, but all of the concepts in here are extremely essential, and the true solution turns out to be really elegant, and I really want to show you that. I'm assuming you guys have read this problem already and already know what it's talking about. However, in case you haven't, let me give a brief summary. So my personal summary is that you basically have a sorted array of numbers that represent where you can cut a log. And in this case, for the sample test case, it's from 3 to 21. And if you think about it in terms of a log, right? If you think about it in terms of a log, then you can cut it at the location of 3. You can cut at the location of 6. Da 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 da. And this final one indicates that you can find this final one indicates as 21. Right? So, and yeah, so you can cut it anywhere along this branch, and the eventual goal, is to somehow make sure that we can count how many ways, right, this person can cut it such that all of the logs, right, all the logs that he cuts are going to be greater or equal to the length of k. Okay? So, and let me see. At least, or I'm calling it k here, but on the problem, k is equal to p. So I'll call it k here now. So we want all the logs to be greater than or equal to k. Now, if we just think about this like sort of naively, right? So I'm going to go ahead and erase it since this brief summary is done. Let's go back to this pointer. So if you think about this sort of like naively, one way some people might want to do this is say, well, the first thought that really comes to mind is say, well, what if we sort of, I don't know, like what if we sort of divide it in the middle, and then we checked if this is greater than k, and if this is greater than k, right? It's actually very hard to do with a brute force solution, because there's like so many different ways you can cut it, right? You can cut it from, you know, from the start to this certain index, right, called I. Maybe we'll call this index A, right? And you can cut it from A to B, right? You can cut it all the way to B. You can cut it from C, right? But and there's so many ways to cut it, and if you were to do this mathematically, the number of ways you can totally cut this thing is 2 to the power of however many cuts there are, right? If n is 7, right, then you can cut it 2 to the power of 7 different ways, because for each of these different cuts, you can choose whether you cut it or you don't cut it, right? So obviously this isn't going to work, right? If we have an n that is large as, 10k, right, 2 to the power of 10k is extremely large. So obviously there must be a better way to do this. So let's think about a better way to do this. A better way is to say, well, better way is to say that, give me a second. I'm still on eraser mode, sorry. A better way is to say, well, we can notice a few things. Well, first of all, all of our cuts, they must be greater than k, right? We can exploit this, right? And the second thing is that if we cut it in that many different ways, right, there's many cases where we can save a lot of different there's many ways we can save a lot of like computation, because let's say you have this fixed interval, right? If you have this fixed interval, this is going to be the same, right? This log is going to be the same, Meanwhile, you still have to search all of those. Why don't we just fix this and then record what the answer to all of whatever these are, and then we can go with a faster solution, right? So this is the kind of like idea behind this problem. You got to think about what are like sort of like the sub problems we can solve such that we can sort of get a larger solution. So in this case, um, what you do is you say, well, first of all, logs that are cuts. Oh shoot, I'm still on this one. Okay, so first of all, cuts that are smaller than k, right? If you go from 0 to, you know, maybe something like k minus 1, right? If a cut is at k minus 1, all of these can be disregarded because these cuts, any cut that starts from any cut that has 1 inside here, absolutely useless to us because the moment you cut something from 0 to k minus 1, you end up with a log that's smaller than, you know, k minus 1, right? So you end up with you'll end up with a log that's smaller than k. So if you end up with a log that's smaller than k, then that's not a valid solution. So it doesn't matter there. So we can start our search at k, right? We don't need to start it at, you know, some arbitrary index in the middle, right? So that's the first thing, right? The first idea is, well, we just start at k, right? We start from what? We start from k. That's the first idea. We need to start from k. The second idea is, well, let's say we're at a middle index, right? Since we can't be at the start anymore because we're starting from this arbitrary k, and this arbitrary k, well, it has to be greater than, you know, 0, right? Because the reason it has to be greater than 0 is because, you know, the first technical cut is at 0. So let's say we're at this arbitrary index, right? If we're at this arbitrary index, then what we can do is we can say, hey, why don't we select a block, right? This block that is smaller than, that is greater than or equal to k, and we have this and we store this block, right? That is just equal to k, or like just greater than or equal to k. This is the smallest block we can have, and the number of ways that you can store the log, or the number of ways that you can partition the log from here is totally unique. So the number of ways at this large point, right? This large log that we'll call from 0 to I, right? And we'll call this smaller log 0 to j, right? So the number of ways from 0 to I, right? So the number of ways from 0 to I is equal to the number of ways from 0 to j, or it consists of the number of ways equal to j. So the number of ways, the number of ways from 0 to I consists of the number of the ways from 0 to j. Are there any other ways we can partition 0 to I? Well, of course, because this is the smallest, right? This is the smallest way we can do it. And obviously, this is also probably going to be the largest number of ways occurring in this way, right? But if you just move this this boundary by 1 over, you just move this boundary by 1 over, right? This is still going to be greater than or equal to k. This length of this is still going to be greater than or equal to k. Listen, so the important part is that this part is still going to be, this configuration still needs to be counted. So from 0 to I, you also do, from 0 to I also equals to 0 to j minus 1. And you can keep doing this until k, right? Once you get to k, then then dividing it any further is no use, because the number of ways to partition from there becomes 0, right? So yeah. So what's the complexity of? Okay, so let's formalize this. This is still very like in the very not very like it's still very abstract, right? Let's formulate this and oh shoot. Let's formulate this so that we can start to discover how to write the code, right? Well, formulating this, we basically have that, well, let's say we were at, okay, hold on, give me a second. Let's say we are at DP, let's say we make an array, we call that DP, and we go from 0 to k, right? Then the number of ways is just 1, because you can't partition this any smaller. If you end at k, right? If you end at k, then there's only one way to partition it, okay? That makes sense, right? So this is our base case. And our second thing is our transition, right? If it ends at I, right? If our DP ends at I, then the number of different ways we can do it is from, if we start at 0 all the way to this boundary, right? So remember what I talked about here. I talked about that it goes from, this some boundary. We'll call it this boundary B, and we'll end at, I, right? Then it's all the way from here, right? It's all of these different ways here, right? So, B minus 1, right? It can't be B itself. And understand why. Because if it ends at B, then we have something that's smaller. Remember, we can only partition it if B is included in this array. So it's B minus 1, B minus 2, etc., right? So it's equal to the going all the way to I. So let's call this J, right? J going to approaching or going to. Am I doing this correctly? Is this how you write something? No, I don't think so. J is equal to what? I. And J starts from B minus, or J starts from, or no, J goes to B, right? And J is starting from K, right? And really, I just talked about this, but it goes to B minus 1, right? Okay. So we take the summation, right? Actually, let's formulate this like more precisely. It's less than or equal to B, and J starts from K. Then in here we say that let's see. We say that dp equals to dp of j, right? And then we say that dp of I is equal to yada yada, this thing, right? And then yeah, that's it. Okay. So let's go ahead and implement this. So I prepared the thing here, and let's go ahead and copy the test case into our file. Okay. So let's name this log, right? Or wood.cpp, and let's copy it in some of our templates here. So we need to read in all test cases. Yeah. To read in all test cases.
I was wondering if you spoke to your husband yet about redoing the air control system.
So if you think about it, you just do this, right? And then you do this. We're talking right now, so I have to be a little bit quiet. And now we just read in the two values that dictate our problem, n and k. So we read in n and k. Now once we read in n, k, we have to read in the values, right? So we do the cuts. Okay, and what we do is we say for int I equals 0, I system n, I plus plus, right? we start from k, right? So I want to find the minimum index to start. Start is equal to 0, right? That's our base case. If there's just one value, then we just start from k. And so if cut to start is valued in k, or yeah, valued in k, then we say that start equals to min of start and I. Right? This basically ensures that we get the first index where cuts is where cuts is greater than or equal to k, right? And let's make a little DP array. Let's make a little DP array, right? And we say that DP of start is equal to 1 because there is one way to partition it from start, or when it equals to k. So now we write the for loop, right? Shut, I'm done. So that while, you know, let's make a pointer here. The pointer represents our boundary. So our boundary is equal to 0. Okay, so let's make it outside of the loop. So here's a little point, right? Little point where we can save some time, right? So let's say our previous boundary is right here, right? We don't have to research the boundary from 0 because we can just start from our original boundary and move forward because because it's increasing. So if this boundary used to be it, then the new boundary would have to be in front of us. So we don't have to put it back to 0. So we can just keep a pointer of the boundary. So while b is less than n, right? We don't want it to go out of the array. And what? And cut the I minus cut the b, right? If cut the I is minus cut the b is greater than or equal to k, right? So what I'm trying to say here is if it's still greater than, if it's still greater than or equal to k, then we can still move the pointer, right? If it's equal to k, can we still move the pointer? I think so. Let's see what's wrong here. Oh, cuts, sorry. Aimed at cuts, whoops. Okay, so now what we do is, oh yeah, we need to start from start, not 0. And for what we can do is, we can say that dp of I is just simply equal to all of the things from start to, so j is equal to start, right? And j is less than I, and j plus plus, right? Not exactly. Equals to start, then b, not I. So we're going to the boundary, right? And so dp of j is equal to is plus equals to dp of I plus equals to dp of j, right? That should be it. Am I doing anything wrong here? Let me think about this. So it goes from start, right? It goes from start and it ends at right less than b. So b is the point where it's b is the point where d is the point where it starts to become less than k. So it can never go to b. It's all the way to b minus 1. Okay, that sounds about right. And yeah, that's literally it. That's literally it for sort of a naive implementation. That's all you would need to do. You just count the n minus 1 and copy this. Oh, I already copied it here. Oops. Okay, so I'm not piping it. I need to pipe it to the file. Okay, so there seems to be an issue here. What's the issue? Let me think. It goes towards K. Oh, I see. So we are not considering 0 to be like a valid cut here. So we need to consider 0 to be a valid cut. So what we can do is we can say this. Cut to 0 equals 0. And we say that equals 1, right? And what we can say is that, well, we send the cut, right? And if cut start now, okay? And then you put I plus 1. Yeah, that makes sense. Okay, and we start from start. Yeah, and we end at n. So we need to consider 0 a cut as well. That's the problem. That should be it. There you go. So considering 0 a cut, we get 3 more cuts. So these 3 more cuts probably are 21 all the way there. Considering not starting at 3, we get 3 more cuts. Yeah, that makes sense. Okay, so let's download. I have the test case downloaded here. Let's download the test case and let's run. Oh, before I do that, I should probably make sure that's modding correctly. So this is just to make sure that it's going to go less than the mod. I think that's about it. Wow, it runs so quickly, right? And I didn't make this one too hard. And you can just simply mod it. Right, and what you can do is you can say, well, after that, you can just count this out. And if you copy this value, right? If you copy this value to the where is my QOTW tab? Ah, there it is. If you copy this value to the QOTW, it'll allow you to submit, which means you got it correct, right? Now, my friends, you may be wondering, right? Is this the most efficient way to do it, right? Can we actually optimize this little code right here? Well, if you think about it, yes, right? We're actually doing a lot of unnecessary computation here. So well, each time we sum it from start to b, right? And we're repeating start, right? We sum start like start to n times, right? N minus start times. And we sum start plus 1, n minus start minus 1 times. So obviously there must be a better way. So what we can actually do here is we can actually get rid of this loop. And we can go for an O of n solution. And actually it's even more elegant. So what you can do is you can make a prefix sum. And I'm not sure if you guys know about prefix sums. So the prefix sum basically stores the sum from 0 to I. And I want to be clear here. I is the true index. So this I, it's an index that starts from 1. So it's like the second element, or the if element, right? So, and what you do is you say, well, prefix the I, right? And prefix the I what? So since we already are on an n scale, what we do is we say prefix the I is equal to prefix the I minus 1, right, plus dp to I. And it's simply elegant. And what we say is that dp of I is plus equals to prefix the I minus 1. Or not I minus 1, b minus 1. Because b is possible, right? So we have to do b minus 1. And let's see. We have to make sure the modulus works, right? And we also have to make sure the modulus works on the prefix sum. Right. So we also have to make sure the modulus works on the prefix sum. Right, so yeah, I think this would also work. If you, oh, something's wrong. Right. Let's see what's wrong. Yes, because the prefix sum actually starts also from 1. So the prefix of the start is equal to 1. Still some issues. So prefix of the start is equal to 1. Yeah, this is embarrassing. I shouldn't be doing this. What if is it B? Because I'm using the true index here. Could be B. No, it's not. Prefix the I equals to. Prefix the I equals to. Prefix the I plus 1. Okay, let me think about this. So, hold on, let me fill this with some goofy like email, right? Let's think about this. So previously what we did was we did from b minus 1. What we did was we summed all the values from k to b minus 1, right? Or start from b minus 1. And what are we doing here then? Why is this one different? Well, let's see. So so the sum from k to k is equal to 1. So that makes sense. The sum of k to k is 1 because k is 1, right? And here what we're doing is we need to go, and here what we're doing is we're saying that dp plus the prefix from, I see why now, okay? So you gotta be careful here. I see. I think I see why now. Right. Does that? The start is correct. It goes from, so the prefix sum computes start again. can't compute start again. It must compute start plus 1. And it must take the prefix sum of now and plus it to there. And it wouldn't be b, it would be b minus 1. I think that's it. What? Oof. We get the famous C++ telling you that you went out of bounds. Oh yeah, we probably should make the prefix a little bit bigger. Count for that. Fudge. Why is this prefix sum not working? So at k plus 1, for example, right? If we're at k plus 1, then we need to sum from, let's say b works. Maybe it's because I'm using b minus 1. It should be b, maybe? I'm confused. No. Prefix sums are so annoying. Alright, let's actually consider this. Let's actually like do some stuff rather than trying to figure this out by changing random variables. Okay, so we did it from b minus 1 to k to b minus 1. So in this case, the sum thing at start, we should only be summing start. Even start is 1, so that works. So then start. So then the next thing, so the dp from, so the prefix from, oh my gosh, this is annoying. The prefix from start to I plus 1, no, that's not it. Because here is computing the prefix from, it wouldn't be I minus 1 for sure.
Stop programming though, bro. Kid thinks he's tough.
Prefix from,
Prefix sum. I know how to do prefix sum. You basically just find the prefix in the sum and you add them.
you find,
Bro, I cannot even see my screen. Oh crap. Good. Did you go to the code forces? Actually?
yeah, I'm recording right now. You start from start is equal to 1.
Holy shit.
That makes sense.
You got minus 9.
Yeah.
Are you retarded? How did you not solve problem Z?
It's interactive. I'm recording, by the way.
Oh my bad.
Maybe I should make this easier on myself and just make it start minus 1. No, but start is the true index. Start is the true index.
Who's bringing back daily problems?
Go away.
Wait, why? Why are you recording?
To solve this one problem. Go away.
What?
Oh my gosh, this is annoying. It's taking me 5 minutes to think about this. I don't see. I'm really confused. From K. You know what it would originally be? It would be 0 to... go from okay, let's see. So prefix the I, right, equals to prefix the I plus the
Bro,
or else how would I
the
encode for
decode
that?
weekly contest?
I think that's it, maybe ish. Fuck. It's still out of bounds. How do you go out of bounds? Oh, start must be. Start can be, so that can't be it either. Oh my gosh, this is making me so dizzy. Okay, let's debug. Prefix sums are always a pain in the ass. Okay, that makes sense. What? Oh, because you do b minus 1, which already, oh, that messes everything up. Ay, ay, ay.
DP.
Okay, so what we can do here is we can say if b minus 1 is less than 0, then we continue. No, we can't continue. Ay, 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 I hate this. I don't like that. Ah, it's still wrong. What is wrong here? This is annoying. The prefix sum is annoying. Okay. It's still going out of bounds. Yeah, it's still going out of bounds, which is messing everything up. It's 8 now. That is crazy. Totally 8? I love how 8 just comes to haunt me. Why is this annoying? And you disappear. Oh, and then the I plus 1 issue. You can't. It's I plus 1 equals to proof I. Okay, that makes less sense. Oh my god. What is this, bro? This is just haunting me at this point. I don't like prefix sums at all. Okay. The DP is computed. It's 1 higher than what I need it to be. That's the problem. Ooh. Oh my gosh. You know what? Maybe I should just make it into B and avoid all these problems. I don't like prefix sums. We do not like prefix sums. Ah, that's annoying. I cannot get this prefix. This is literal rage bait. This prefix sum is literal rage bait. It's just literal rage bait. How can I get the DP to work but not the prefix sum? Did it modify the Oh, I think I know why now. I think I know why now. I think I may know why now. And I think that might be the issue. And we don't have to do that, because we already computed the dp for a start. Why are we computing it again? The dp of I is equal to dp of I minus 1. dp brief I. Oh my gosh, I don't like this prefix sum, because I can never get it to work. Kids, this is why you don't do unnecessary. Optimization is the root of all evil. This is why optimization is the root of all evil. Oh my gosh, and now we have this issue.
Major.
Oh my gosh. How can b minus 1 be so low?
你叫我了吗？
I cannot believe this. I cannot believe this. I will get this to work, guys. Trust me. I will get this to work. And it doesn't work anymore, because b minus 1 is always less than 0. No, it's greater.
I hate math so much.
There you go, guys. Okay, I think I understand why it went issue now. So what I did before is I started at start, and the reason that worked was because I was going from j minus 1 to j. But anyways, my point is you can do this with prefix sums, and it's really annoying, but it's much shorter. As you can see here, it's like really much shorter. Alright, good luck and happy coding.